strong acids and weak acids, and strong acids and weak bases. So let's talk about strong acids. Strong acid makes you think that maybe this is a powerful acid or it's more corrosive or something, and that's not the case. The word strong here is used in the same way as we used it with electrolytes. A strong acid is one that ionizes completely. So HCl is a strong acid. HF and HCl look similar, right? They're hydrogen ions with a halogen, and they're right next to each other in the periodic table, and you think, oh, these guys are similar, right? And yet one's a strong acid and one's a weak acid. HCl is a strong acid, it ionizes completely. HF is considered a weak acid because it does not ionize completely. And yet HF is actually much more corrosive and dangerous than hydrochloric acid. So here's an illustration. We put hydrochloric acid into water and it ionizes completely. We don't see any HCl molecules left. And here's showing pictures of what these are doing. So this is a model of the HCl, and when it comes into the water, all the hydrogen ions jump on a water molecule, forming a hydronium ion, and the chloride ions are swimming around, surrounded by water molecules, attracted to them, but not actually forming a molecule with them or an ion.
Does that mean that when you drop a hydrochloric acid into like a solution, that solution becomes more acidic than if it was a weak acid you're dropping into it?
Yes. Yeah. So here is the chemical equation. So HCl plus water. This is the acid. The acid is a proton donor. Water is acting as the base, the proton acceptor. And so we get the hydronium ion and then a chloride ion. And here, this is a single arrow, and that means the reaction goes to completion. It's not an equilibrium, it goes all the way to the right. So strong acids are also strong electrolytes. A strong electrolyte is something that ionizes completely and conducts electricity well. So if we have a 1.0 molar HCl solution, we can see from the equation that all of this HCl is going to form hydronium ion and chloride ion. So whatever the number of moles per liter of HCl, we're going to have the hydronium ion concentration be the same as that. It's all going to form hydronium ion. And when we put things in brackets, we kind of learned this in chapter 15. When we put things in brackets, like an X, that means molar concentration of X. So whatever's in the brackets, we're talking about the molar concentration of that. It's kind of a shorthand. And we did a demonstration of this in lab last week. Here is a conductivity apparatus with the electrodes submerged in pure water, and this is attached to an outlet, and the light bulb does not go on because pure water doesn't conduct electricity. There are no ions or charged species to carry the current. If you put hydrochloric acid into this water, now you have hydronium ions and chloride ions, and they will carry the charge, and this is a strong electrolyte, and the light bulb goes on. There are, well, depending on which book you look at, this book says there's 6, some say there's 7 strong acids. So there's a short list of strong acids, everything else is a weak acid. If we look at these, some of them are pretty similar. Here we've got HCl, HBr, HI. Those are all halogens with hydrogen ion. And here we've got nitric acid and perchloric acid. All of these guys have one hydrogen. These are considered monoprotic acids. As we said, a hydrogen ion is a proton. And we write it with that ionizable hydrogen ion, the one that comes off of the molecule, first. And so all of these have one hydrogen ion. We say they're monoprotic acids because they have one ionizable hydrogen, or one ionizable proton. Just 2 little letters different. Sulfuric acid, though, is a little different, isn't it? It's H2SO4. This is a diprotic acid. The prefix di meaning 2. It's got 2 ionizable protons.
Does it just keep going up?
two-proton acid.
Triprotic.
There are also
Quadprotic.
triprotic, yeah. I don't know that there's any quadriprotic or tetraprotic acids.
Pentaprotic.
It does not make them stronger, no.
Does it increase their ability to dissolve or to
When sulfuric acid ionizes in water, it forms twice as many hydrogen ions per mole.
That makes the fluid more acidic?
It makes it more acidic, yes. But the strength of the acid is, does it ionize completely? And all of these do. Weak
Do they make it
acids,
faster-
you
do
know,
they
no.
make it faster or slower if it's diproduct as opposed to monoproduct?
Faster or slower, that doesn't
And if
make
you
sense.
dropped it, would it dissolve, would it ionize faster or slower?
Not necessarily, no. They're all gonna ionize pretty quickly. Weak acids do not completely ionize. So they contain few ions. They do contain some ions, but they only contain a few. So they are what are considered weak electrolytes. They conduct electricity, but they don't do it very well. So weak acid, weak electrolyte. So HF is a weak acid, and we look at its reaction here with water. Again, it's an acid. It donates a proton to the water, which forms hydronium ion, and what we have left is fluoride ion. But here we have that double arrow, the equilibrium situation. And so there's an equilibrium here. And remember, an equilibrium does not mean that you have equal concentrations on each side. It just means that the reaction is proceeding in both directions, and we can affect which side it lies on by messing with concentrations and things.
It's because the fluorine is the most electronegative, and so it's ripping the hydrogen away and forcing it back into the HF.
We really don't, I don't really know any explanation, easy to understand explanation for why those strong acids are strong acids and the rest of them are weak. I can't really give you a satisfactory answer, sorry. You'll have to take some more chemistry classes. I mean, you talk to my husband, he probably knows. He knows all kinds of crazy things. But then he can't find his sweatshirt, so. It's like, there's a good side and a bad side to everything. So when you put hydrogen fluoride or hydrofluoric acid into water, it does ionize a little bit. So here we have, in this example, is showing one hydronium ion and one fluoride ion, but we also have the intact molecules. With a strong acid, you really don't have any of those left. So here with the model, here's the model HF, and when we put it in here, one of the four comes apart, and the other three are intact. Okay, so that's the difference between a strong acid and a weak acid. Conductivity, the weak acid is a weak electrolyte. So here's the pure water again. You put hydrofluoric acid in there, and the light bulb glows, but not very well. It glows weakly. Weak acid, weak electrolyte, weak light bulb.
But because it does not break apart or ionize as easily, does that make that remains the concentration is higher though of it particular rather than raising just the pH of the solution?
If you put the same number of moles of weak acid in a solution as strong acid, the pH, the acidity level of, forget pH, we haven't talked about that. The acidity level of the strong acid will be greater than the acidity level of the weak
So
acid.
the concentration of the weak acid will remain, correct? Since it is not ionized.
The concentration of the intact molecules will be relatively high.
Yeah.
Yeah. So here are examples of some weak acids: hydrofluoric acid, acetic acid, formic acid, sulfurous, carbonic, and phosphoric. So sulfurous acid is similar to sulfuric acid, right? Just differs in the one oxygen here. This is also a diprotic acid, it's H2. Carbonic acid, H2CO3, diprotic. Phosphoric acid has 3 hydrogen ions. This is a triprotic acid. It's got 3 ionizable.
So that's fully ionizable, right? Everything ionizes in?
It's ionizable. It's able to be ionized, it doesn't necessarily
So not-
ionize.
So not necessarily all three hydrogens are gonna turn to ions?
Right. So when you
Okay.
put phosphoric acid into water, and actually this happens with sulfuric acid, and it says here at the bottom. Sulfuric acid is listed with the strong acids because the first hydrogen ion comes off completely. The second one, though, only comes off partially. And so they come off one at a time. It's not an all or nothing thing. So the phosphoric acid is a weak acid. So you'll have intact H3PO4 molecules. You'll also have some H2PO4 minus and some HPO4 2 minus and some PO4 3 minus. So they come off individually. And Chem 2 is where you learn more than you want to know about that.
If that one were to ionize completely without question, then it would be extremely strong acid, right? But since it doesn't ionize completely, it's not?
See, there's a difference between high concentration and acidity and corrosiveness and whether it's a strong or a weak acid. And that's a hard distinction to make because you think, oh, weak acid, that's not really very harmful at all. But if it's a really concentrated weak acid, it could really, really hurt you. Whereas a low concentration of a strong acid may not be harmful to you at all. So the strong and the weak have only to do with how much it ionizes.
On the weak acid, would it make a large enough difference if we increase the thermal energy and force them apart?
You can cause a weak acid to ionize more or less because it's in equilibrium. So everything that affects equilibriums will affect how much it ionizes. And so it'll ionize to different degrees at different temperatures.
So, yeah.
To serve as like an electrolyte, does there need to be water present? Because I know in car batteries it's like 75% water. Is that for the acid to be able to transfer electricity at all?
Generally, yes. See, there are very few substances, especially ionic substances, that would be liquid at room temperature. And if it's not a liquid, the particles, the ions aren't free to move, and so they cannot conduct electricity. When you dissolve them in water, water gives them the freedom to move. Now, sodium chloride can be melted, but it melts at a very high temperature. When it is melted, it conducts electricity. But you wouldn't want to have to sustain that high temperature in your car battery for it to work. So yes, water is present in most solutions that are conductive. Any other questions? You guys ask good questions.
You have good answers.
Well, thank you. Thank you. So let's
You still not answered the one question I asked.
let's look at these illustrations. Which one of these is a weak acid? Like, what are we looking at here? Well, let's look at beaker A. So what do we have in beaker A? We have two kinds of particles, right? We have these hydronium ions and we have the iodide ions. So that is fully ionized. There's no HI. There's no white and blue molecules. So this is a strong acid. It ionized completely. How about this one? For it to be a weak acid, there would have to be three different kinds of little structures there. And so maybe, oops, sorry. I like to point on the larger part of my screen, but it doesn't work. So it looks like there's only two different kinds here, right? So that's going to be a strong acid also. And then over here we've got hydronium ions, and we've got formate ions, and we've got formic acid molecules. So a lot of these HCHO2s did not come apart. They did not ionize. That's a weak acid. So,
Would there be a weak acid as well?
no. Because there's only two kinds of particles. It ionized completely. So the answer is C. It's something here. So this is the one that's a weak acid. So again, try to separate corrosiveness, concentration, from this idea of strong and weak acids. Strong acids ionize completely. Think of it in terms of the electrolytes in the light bulb. Strong light, strong electrolyte, strong acid. Weak light, weak electrolyte, weak acid. And then there are non-electrolytes, and they don't light the light bulb at all, like sugar.
You could technically make a weak acid just as, make a light bulb glow completely by just bumping up the concentration because that bumps up the ionized.
Yes, if you
fraction.
made the concentration of the acid much, much higher,
Mhm.
then you would have more ions, and so it would conduct more. But if you're comparing similar concentrations, the weak acid will conduct much more weakly than the strong acid. So let's do this example. So what is the hydrogen ion concentration in each of these solutions?
42.
42. Yeah. Well, it's the answer to everything, right? Life, universe, and everything. No, not this one. So to answer a question like this, we have to be careful. In a strong acid, the concentration of the hydronium ions will equal the concentration of the acid, but in a weak acid, it will not. So we have to identify, is this a weak acid or a strong acid? The strong acids were HCl, HBr, HI, perchloric acid, nitric acid, and sulfuric acid. Is this one of them? No. This is a weak acid.
Is there a way to do that other than the knowledge of those, so we can break it down?
No. I'll give you the list of strong acids. How's that? So can we know what the hydronium ion concentration is for this guy? We don't know how much he ionizes. So all you can say, and I'm going to change colors here because I didn't mean to be writing in red. All you can say for this guy is that the hydronium ion concentration is going to be less than this. That's all you can say. In Chem 2, you will learn how to calculate that. But it has to do with an equilibrium constant. Okay? And it's,
So
yeah, we call it, it's called Ka, but it's a solubility product constant sort of thing.
Is Chem 2 calculus based or is it just algebra?
I do not believe that Chem 2 is calculus based. There is some solving of quadratic equations sort of thing. There's some hairy math stuff, but they do a lot of approximations too to get around stuff like that. Okay, so what about HI? Is HI a strong acid?
Yes.
Yes, it is. HI is a strong acid. So then the hydronium ion concentration is equal to the concentration. Oops, my decimal got lost. 1.25 molar. Because all of the HI ionizes. And so the hydronium ion concentration equals what you put in terms of the HI. And then we can also say, well, the iodide ion concentration is also equal to 1.25. How about HF? Strong acid, weak acid?
Weak acid.
Weak acid.
So
So hydronium ion concentration is what?
less than 0.75.
Less than 0.75. That's easy, huh?
Did you understand?
Once you understand. You're brilliant, Andrew. It's easy once you understand. Until you understand, not so much. And the problem is, I would say the majority of students go through their whatever chemistry classes they have, and they don't understand most of it. And I remember I took honors chemistry in high school, and I got an A in it, but I felt like I had no idea what I was doing. I'm like, what on earth? The good news is, when I went to college then and took, it would be like Chem 1 here, then all of a sudden everything started to fall into place. And I'm like, oh, that's what they meant. Oh, I said oh a lot that semester. So the second time you hear it, it makes a lot more sense. Yeah, the light bulbs, yeah. Right now, some of you are weak electrolytes. You just have this little glowing bulb that's just barely glowing. We want you all to be strong electrolytes by the end of the semester. So we talked about strong acids and weak acids, and the same concept applies to bases. We have strong bases. A strong base is one that completely dissociates. And here are some examples of strong bases. There are some of these bases contain two hydroxide ions. These guys, strontium, calcium, barium. Now we mentioned that the diprotic, triprotic acids, those ionizable hydrogens, come off one at a time. That doesn't happen with the bases. They all come off. They either all come off or none of them come off. So the bases are a little bit different that way. So here's an illustration. Sodium hydroxide is a strong base. You put it in water, it all breaks into ions. You don't have any intact molecules left. Weak bases. Weak bases are like weak acids. We're most familiar with thinking of bases as being metal hydroxides, because we see, well, if that dissolves, it's going to create hydroxide ions. That's the Arrhenius definition of a base. But then there's also the Bronsted-Lowry definition of a base, where a base is a hydrogen ion or a proton acceptor. Most of the weak bases are going to fall into that latter category. They're proton acceptors, and it may not at all be obvious that they are a base. And so here's just a general equation for those weak bases. When they react with water, they accept a hydrogen ion and form hydroxide. The hydroxide doesn't come from the base, it's actually from the water. Whereas with those strong bases, they had hydroxide ions in them, and so they directly release hydroxide ions. So we tell you about weak bases, but we don't do a lot with them, because they're just a little bit more complicated. Ammonia is probably the most familiar weak base. And you look at ammonia and you're like, that doesn't look like a base. Well, this is probably I think this might be the only one that you really need to know. This is a base. And this forms NH4 plus ions in solution. And so we're familiar, we learned what ammonia was. It has a special name. We don't call it nitrogen trihydride. And this NH4 was one of the ones we had to memorize, which is ammonium ion. So when you put ammonia in water, you get a little bit of ionization. And that's why sometimes a solution of ammonia is called ammonium hydroxide. Because if you had ammonium hydroxide and you put it in the water, you'd get the same effect. And here in the picture we see that only a little bit of them actually comes apart, ionizes. There are a lot of weak bases. Just like with the acids, there's a lot more of the weak ones than the strong ones. And a lot of them are organic amines, and this is just kind of for your information. So there's ammonia. You should be able to recognize that guy. These guys are kind of weird organic things. And then bicarbonate ion is another one. So HCO3 minus, well, that can accept a hydrogen ion and become carbonic acid. Remember we talked about how these were conjugate acid-base pairs. Here's the base version and this is the acid version. Yes?
I thought the carbonic acid was unstable, so it would break down to water.
Carbonic acid is unstable.
So wouldn't it make water and CO2 before it could ionize anything further?
There would be some present. I don't think it would all fall apart. There would be some present. The fact is that we do lie to you in beginning chemistry. It's for your own good, okay? It is. If you want to find the truth, you have to keep taking chemistry classes.
Walk out.
I have to keep re-editing.
Okay, so
These boxes, this is a lie.
this is a lie. They lied to me.
The question is, are you lying to us or are they lying to us?
I'm sharing their lies.
Makes her part of the problem.
She's part of
I
it.
am part of the problem. I'm
You
sorry.
just told me that Santa's not real, but they keep believing in him for this moment.
It's
Exactly.
kind of hard.
Wait, what's that?
Should've
Santa.
told me at the end, you should have said like finals, we're taking tests as we turn in,
You
just so you know.
So, the kids ask, is Santa real? And I said, well, what do you think?
Gilly, it's a feeling. It's like that pseudo before you tell them, no, it's not real, sorry.
So we can do questions like this. Never tell kids no.
I just tell them, no.
Well, I don't want to flat
It's
out
a lie. Sorry.
lie to them.
Welcome to a cold reality.
Santa is
Gilder
real. It's
Tyler
called
has been on
Saint Nicholas, and he's not alive anymore.
But see, their meaning is the whole thing of him coming down the chimney and bringing me presents reels. That's what they're implying.
I don't know that.
So what is the hydroxide ion concentration in each of these solutions? 0.055 molar barium hydroxide. Is that a strong base? The metal hydroxides are strong bases.
Yes.
Okay.
Yes, this is a strong base.
No,
She's gonna put that on the test.
Oh, so cation based ones are going to be strong.
The ones where you see OH, those are strong.
Okay.
Okay, that's your little rule of thumb.
But you said metal based ones are always going to be strong.
These are the only ones with OH like that in them that you'll see are metal hydroxides.
Okay, that one.
Yeah.
It's like the sodium.
Well, I take that back. There's ammonium hydroxide. They're ionic compounds with hydroxide.
Is ammonium hydroxide also strong now?
No, it isn't.
So OH is always strong except for if it's with ammonium.
So only metal hydroxides. Yeah, sorry.
It's like a poly.
It's one of those things that I just kind of know and I don't think about very much. So the hydroxide ion concentration in a strong base is going to be the same as the concentration of the base. What was that? How about this, C5H5N? That's gonna-
the hydrogen.
That's going to be a weak base. The nitrogen is what accepts the hydrogen.
So does it turn to C5H5NH
Plus.
plus? That's what turns into a.
Or, we're not going to get into the subtleties of that. If you wrote C5H6N plus,
But
that-
it turns into two different.
see, the nitrogen on here
and
This
then
is
it
the
turns
rest of the
into NH
molecule.
plus, right?
has a lone pair.
Yeah.
See, and water, when it accepted a hydrogen ion, the water came and held on to the lone pair. And so when this forms an acid, because it's a base, it can accept a proton, when it does that, it becomes an acid, then you get a plus charge and you got this hydrogen ion that's sitting on that lone pair of nitrogen. That's what happens.
But when you have the water, does it literally give up the hydrogen so it no longer is covalently bonded to it?
Right, so the water, so there you've got water, and that will give this hydrogen ion, it keeps its electrons. It says, well, hey, little proton, if you want to leave, you're fine, but I'm keeping the electrons. So this hydrogen goes over here, and that's not what I wanted to do, and what you end up with is hydroxide ion.
And so since it has the positive proton, then, so it's pretty much just, that's why you call it a proton, because it's just a proton.
It is literally a proton.
It's hydrogen, because hydrogen is so little, it's
Right.
literally, you can almost not think of it as an atom anymore.
Exactly. So a hydrogen atom is one proton, one electron. You take away the electron, all you have is a
So
proton.
does the proton, where does the proton go when it bonds? Does it bond like on the outside, or does it go to the nucleus of the new atom?
It acts just like these other hydrogens that are sharing an electron with the nitrogen. It's going to share these two electrons, but both of those electrons originally belong to the nitrogen. So it's like, hey, I like your lunch, let's share. I'm not bringing any to share, it's not mutual, but you're going to share your lunch with me.
What if so this is a situation in which it's being dropped into pure deionized water, right? Completely and totally pure. 'Cause what do
It
we
would
do
happen in just any kind of
So
water.
what do we do when we have something like free-floating sodium ions? They're going to be coming by and saying, what's up?
Yeah, they'll wave and then they'll keep going. Because the sodium ions are soluble in the water. They're surrounded by water molecules. that are showing them their negative side. And so it's not attracted to these other
Well,
things.
what about like, what was it, like the magnesium carbonate?
If you get something like that,
Like,
yes.
what's up? And it's like, let's have some fun.
Yeah,
I
so
wanna-
if you end up with two ions that form an insoluble ionic compound, yes, they will precipitate out of solution. And that does have implications in real life, with hard water in your washing machine and it precipitates out some of the soap and it just makes things not very good. So, okay, so this is a weak acid. I'm just going to erase all those scribblings. That's a very slow way to do it. Let's go like this. Because shouldn't it make a squeaking sound? You don't have to answer that. So the hydroxide ion concentration is less than 1.05 molar. That's all we can say. Sodium hydroxide, strong or weak?
Strong.
Strong. It's a strong base. So then the hydroxide ion concentration is just equal to that.